So when we talk about center of mass, we're talking about a location in space. The meter stick is simple. The meter stick, I can point at it and say the center of mass is in the middle of the meter stick. At least pretty close. It's actually not quite at 50, but somewhere around the middle is a center of mass, but it's a place. Now, I want to talk to you about how we calculate center of mass, but you can find the center of mass just by balancing something. If you balance it, it will balance at its center of mass. Now, it's easy to balance a meter stick. First, it's very linear. You have to assume that any object, regardless of its shape, has a center of mass. And if the object's shape can change, then its center of mass can move. You follow what I'm saying? If I have a paper clip and I change the way it's bent, I am changing where the center of mass of the paper clip is. Because center of mass is about the distribution of the mass. So how it's shaped. A donut probably has a center of mass somewhere in its middle where there is no donut. Unless it's a jelly-filled donut. Then there might be some jelly there where the center of mass is. But at the same time, something as simple as a meter stick or a block, something has a center of mass probably in its middle. Understand that because the meter stick is linear, its center of mass can probably be described by like X. But if I'm dealing with something that's finding center of mass can be done experimentally. I've just shown you how to do it. But you can also do it mathematically, but I want to be honest with you. The mathematical way is going to freak you out a little bit. When I say that, it's going to have to put symbols and stuff here. So I want to show you what the center of mass formula looks like, and I'll just show you the one-dimensional version of it. If I remember right, this is on your equation sheet. So this is the equation for center of mass. And it's not particularly useful, and we're not going to use it. You will not be called to do this semester. You will be called to do it next semester. It's been on the exam in this form maybe 3 times in the last 15 years. It doesn't show up often. And every time it's shown up in the last 2 exams, they've given you the answer. So if you can't do the integration part, you just skip it. Take their answer and move on. There'll be a question that'll sound like, show that the center of mass is here. And then they'll say, they'll give you the expression. Now, I know that you guys don't know much about calculus, all of you, but this symbol means to sum every piece of mass, taking into account its location. That's what that says. So again, if you're taking notes and you want them to mean something, this symbol means sum, add up. This part is each piece of mass, dm, delta m, piece of mass. X, location. So the top part is just adding up every piece of mass, taking into account each piece of mass location. The bottom just says to add up every piece of mass. So the bottom is very likely the mass of the object. That's all it is. The reason the sum is there is sometimes you don't know what the total mass is. Maybe they give you the mass as an expression. Maybe different shaped, then I would probably have to define its center of mass by x and y. So a center of mass in the x direction and a center of mass in the y direction. And you can probably imagine if we go to a 3-dimensional object, the center of mass could be described as x, y, and z. So again, it's a location. And that should tell you more. It's also got to be a vector because all locations are vectors. But again, I'm going to do it this way, right? I'm going to write things down. I'm going to look at you in the eyes, and I'm going to say things. In the end, I can explain it again, but I don't know if it'll make any difference. And that's kind of how I feel right now. Because I've said it. and more than once about each of these things. And I'm not sure where the disconnect is. Like, you could ask that same question about why and when would I use these two things. If you recall, and I don't mean this mean, we use this to derive this. I'm not sure, but it's just letters, right? But they're based on some meaning here. This represents the force of gravity acting on an object. We took that object, placed it somewhere in our universe, and said that near the surface, not somewhere in our universe, near the surface of the Earth, we said that this object is experiencing a constant downwards force due to gravity, and you were somehow able to move that object upwards from its starting position of h naught to its final position of h, that the work done would be equal to minus g h minus h naught, so minus mg h minus h naught, and that the change in potential energy would be equal to minus the work done. This is what we did in class. Does this ring a bell of any sort? If it doesn't, then you weren't here that day or weren't paying attention, but we did this. And I say this not in any, I'm not frustrated. I'm saying the reason I'm going about it this way is because the idea was work is the method that something's energy changes. We define work based on any force used during the displacement of an object. That force has to have a component in the direction of the displacement for that force to be doing work. In the case of this object being lifted up, there's probably more than one force doing work. There's probably the force of the object, of the force that's lifting the object. Probably some external agent, a person picks something up and lifts it up. But there are other forces acting, and one of the other forces acting was gravity. And during the course of lifting the object up, a delta x of h minus h naught, a downward force of mg acting on the object, and the angle between the force and the displacement being 180 degrees. Right? That's the parts of our definition of work. So this is not a first principle. This is a definition. We are defining work this way. That's what physicists have defined it like this. And we did work lifting the object, but gravity did a negative amount of work while the object was being lifted. So we know something is different about the object because if I drop the object, I can get that energy back. And so we defined the concept of potential energy as minus the work done by a conservative force, an interaction that takes place between the object and the earth. That's this definition. So once I found the work done, I said I am going to define this as gravitational potential energy. Where'd the negative sign go? It's a definition. It's how we define potential energy. It's minus the work done by a conservative force. Now, I'm bringing all this up because if I ask you to tell me the forces acting on this object, could you do so? If I say the object exists in space, just hanging above the ground someplace, and I say draw a free body diagram, would you know to draw a downward arrow indicating that there is a single force acting on the object downwards called mg? Well, that's when I would use mg. When I'm trying to identify the force of gravity on an object. When will I use mg h minus h naught? Well, probably in a circumstance where I might want to know an object's gravitational potential energy. Maybe I know the object is going to change its height and knowing its potential energy at the two locations it's going to move to might be helpful in finding out something else about the object. Does this all seem reasonable? Now, I'm picking these out because the next thing we're going to do is harder. I defined a linear spring as an object that, when displaced, will attempt to put itself back into its original shape. Remember that conversation? So there are lots of things that obey this principle, but we talk about springs specifically. And I said that an ideal spring has a force that is proportional to its displacement. I use this equation specifically. I called this Hooke's law. And I also used the phrase linear spring a couple of times to describe Hooke's law. It's linear in that it's a direct proportion. If I double the displacement of the spring, I will double the force from the spring trying to push itself back into shape. I said to you too that each part of this force this equation has a specific piece of information contained in it. First, it's about forces. The force of the spring. And I say that we can treat this like a tension or a normal force. If I push a box into the spring, making the spring smaller, then the spring is going to push backwards to try and get the box back to where it started. Now, of course, this is another kind of interaction, and I said without proof that this was a conservative force, because I can't prove to you that it's conservative. I mean, I could, I just don't want to. I'm not sure how I would go about doing that. But I do know that also if I pulled out on the box and I'd stretch the spring would try and pull backwards. Remember that? And you guys have played with springs probably in some way, shape, or form, or at least at the lab, where you hung some stuff on a spring and watched it stretch. Right? In that case, you use the weight to pull the spring outwards, and the thing settled when the upward force from the spring, Kx, was equal to the downward force of weight, mg. Does that sound familiar? All right, that's why I also illuminated the idea that this proportionality constant determines how stiff your spring is or how loose your spring is. A low value here means it'd be easy to pull the spring outwards. A higher value here makes it would be harder to do so. But what's that negative sign mean? It tells you that the force is in the opposite direction of the displacement. If I push the spring to the left, the force from the spring will be to the right. That's what the negative sign indicates. It's a directional thing. Whenever a negative sign is applied to a vector, it's about direction. So that tells us what Hooke's law is about. Now, we found that we can store energy in a spring. And we can do so by maybe pushing the box against the spring and then locking it in place, right? Put a little latch in there or something. Or maybe I'll just hold it there with my hand. And then when I'm ready, I'll just let go of the box. If I do this right, I might be able to get that energy back. So if it's conservative, then us knowing how much work is done by the force of the spring might help us understand how much energy there is stored in the spring. So I said to you, well, we're going to have to do this different because this force isn't constant while we're changing our location. The more I push on the spring, the more force that's required to continue pushing on the spring, right? It's increasing as x increases. So if I want to talk about the spring and how much work is done by the spring, I would say to you that, well, the displacement is in this direction. but the force from the spring will be in that direction. So I would say that I could do the integral from 0 to some capital X, something different than just regular X, some different X, I don't know, of the force from the spring times how much I push in the spring times the cosine of 180 degrees. And then I'd go further and say, all right, well, force from the spring is Kx, and the amount that's displaced in the spring is dx, and the cosine of 180 is -1, and to find out how much work is done, I'm going to have to use the integral here. And I'm not going to belabor this. If you integrate this, you'll get -1/2 kx squared, which has to equal the work done by the spring while it was being compressed. Now, something else probably was pushing on the box to get the spring to be compressed, right? We're not talking about the work done by that force. We're talking about the work done by the spring, because this is a conservative force. And now, because I can define the change in potential energy of the spring box system as minus the work done by the force of the spring, I can define elastic potential energy as 1/2 kx squared. So when would I use each? Well, I'd use this whenever I needed the force from a spring. If I push on a spring and it stretches or compresses, this would tell me how much force the spring would provide. Or maybe it would tell me how much the spring would compress. But if I pull the box back against the spring and I release it, this would tell me how much energy there might be given to the box, because that was the energy stored in the spring. You guys catch all that? Again, I have a little rampy thing with a spring at the bottom. The car I put on the top of it has a mass of 50 grams, and when I release it, it rolls down this hill. When it hits the spring, it compresses the spring 15 centimeters, the maximum compression of the spring. Of course, then it bounces off and shoots back up the hill. What's the spring constant of the spring? And what's the maximum force experienced by the car before it springs back up the ramp? Okay, so I've given you a problem to do. It involves the spring. It involves the spring twice. Once to find the spring constant of the spring, and once to find something else out about the spring. So in my first question, I asked you to figure out what the spring constant of the spring is, because we don't know it. We do know that when the car is down here, the spring is going to be compressed a distance 15 centimeters by the car. That we do know. Barring any energy being released to the environment in the form of friction or air resistance or something, I think this sounds like a conservation of energy question. Sounds that way because I see a clear change in height of the object, and I'm asking about springs. Those are two probably red letter things that suggest I'm going to be dealing with conservation of energy. And if there's nothing here to take the energy out of the system, I think the mgh minus h naught that I have here, the potential energy at the top of this ramp, is likely to be equal to the amount of potential energy stored in the spring when it's at maximum compression, when the car is no longer moving. I know there won't be any gravitational potential energy down here because that's the reference level. I'm setting that as the point in the problem where there is no gravitational potential energy. And I know there's no elastic potential energy up here because there's no springs up here. And I know that sounds silly, but some of you don't know that. And you'll notice I don't have anything in here about kinetic energy because I never asked how fast the car was going. Now, finding out my answer, just pushing buttons, least interesting part of this. But the part that you guys have maybe some amazing success at. So my car is 0.05 because you guys forgot to convert it from grams to kilograms. And G is 10. At least you get that one right most of the time. And H, 1.2 meters. What does that equal? It equals something I don't know because I don't know what K is. But I do know the spring got compressed 15 centimeters, 0.15 meters, of course, because everything needs to be in kilograms, meters, and seconds. Why? Because G is in meters and seconds. Now, this will tell me what K is. Right? I've set the energy at one place equal to the energy at another place. And I'm sure you guys who are rapidly pushing your buttons can tell me, what is K? 52.3 newtons per meter. Don't forget our units here. Now, that's not the end, because then I said how much force was experienced by the car from the spring when it was pushed up against the spring. Well, the maximum force we know has to come when the displacement was maximum, because the force from a spring gets bigger the more the spring is compressed. So the maximum had to occur there. And now that I know what K is, and I was given X, pretty sure I can find it. Am I going to worry about that pesky negative sign? Probably not. I'll probably use it to tell you what direction that force is, though. I think that force is to the left. It's going to push the car back. So the question is, why did we set these two things equal to each other? You remember that? Excellent. What is it?
The work is equal to the change in kinetic energy.
Any work?
Well, the work of the
I don't know. I said it yesterday even, but anybody want to crack a guess here? Or are we too scared because you think Mr. Sheldon's going to lash out irrationally at you? I mean, look, you take your own learning into account here at this point, but your grades aren't going to go up, and that's your issue, not mine. My parents aren't going to yell at me about my grades anymore. Can somebody else tell me what this is, what's important about that W that's different about the other times I write that W? Because if you can't, again, take your own medicine. Yes, sir. Net work, that's right. This is the work done by an unbalanced force. Otherwise, the kinetic energy wouldn't change, right? Kinetic energy can only change if the velocity changes. And the velocity can only change if there's an unbalanced force, because that means there's an acceleration, right? All those things are connected. You can't just talk about one without talking about all of them. So when I say that, I talk about the work done by an unbalanced force. When I release the car, there's clearly an unbalanced force on the car, isn't there? Wait. Nobody said anything to that. Is there an unbalanced force on the car when it was released here? I sure hope so, or it wouldn't roll down the hill, would it? It'd stay there if there was no unbalanced forces. Look, these are easy questions. If these are the ones you can't answer. So I'm saying that because at the same time, the unbalanced force that's causing that is gravity, which is a conservative force. And we just said that work done by a conservative force equals minus delta U. I just put the minus sign on the other side, but it's a definition, right? Okay, so this unbalanced force causes a change in potential energy, which causes a change in kinetic energy. A delta means final minus initial. Still good? Distribute that negative sign. I'm running out of space for this, so. I distribute the negative sign by just reversing them. Is that okay with you guys? Okay. I'm going to get all the F's on one side and all the I's on the other side. And then, like I did 2 weeks ago, I'm going to put a box around this and say that this is important because this is what we call conservation of energy. If nothing takes the energy out of the system, then when we add up all the energy we have at one place in the system, it will have to equal all of the energy in another place in the system. Again, I did start from our first principle, right? The things we said we're supposed to know. I started from there again and said, I bet we could use this to explain something we're going to do. And that's what I used it to explain. That if it's a conservative force and nothing takes energy out of the system, then the energies before equals the energies after. So why did I set those equal to each other? Because when I looked at the car, was the car moving here when I said at the top? No, so there's no kinetic energy. Any spring up there? No, so the only form of energy it has is that it's above the reference level. Why did I put MGH there? It's gravitational potential energy. That's how much energy it has. When it's down at the bottom, stopped against the spring, does it have any kinetic energy? No. Does it have any potential energy due to gravity? No. Is it pushed up against a spring? Yes. If nothing took the energy out, they have to be equal.